Welcome to the lecture 2 of the lecture series on the enzymes used in recombinant DNA technology. Today's lecture it is on the restriction endonucleases 2 or the type 2 restriction enzymes. The restriction endonucleases 2 or the type 2 restriction enzymes, it is going to cut the DNA at a specific site only, and it is going to cleave the double stranded DNA which is of the B form of the DNA. That is, it is not going to cleave the Z form of the DNA and the A form of the DNA. The restriction site has the rotational symmetry, that is, it is a palindromic sequence and the different enzyme recognizing the different sequences. Now here you can see that and there is a restriction site. Here it is a GAATTC, and this one it is an axis of symmetry. And when you look at this sequence, read it from any one of the end from the strand of the DNA, it is the same one, like how GAATTC, and from read from this GAATTC. That is, read from any one, it is the same one. That's why it is going to be called as an palindromic sequence, and symmetry, it is a rotational symmetry. Now here the example it is of the EcoR1. When you look at the restriction site of the EcoR1, it is the GAATTC. Okay, so this oblique symbol it denotes that here it is a cutting site or the cleavage site or the restriction site. Okay, this it is a cleavage site where the enzyme it is going to cleave the DNA. Okay, and this asterisk symbol it is going to show that there is a methylation by the methyl transferases or the methylases, which are the cognate EcoR1 methyl transferases or the methylases. So this restriction site, when it is a methylated at these A sequences, okay, at this A bases, at that time the EcoR1 restriction enzyme it cannot act on this restriction site. But if it is the unmethylated one, at that time it is going to cleave in between the G and A. Thus, the restriction enzymes, okay, thus the restriction enzyme, most of the time, they are going to cleave the restriction sites which are the unmethylated DNA sequences. The methylated DNA sequences, they are not going to be cleaved by the restriction enzyme in some of the cases. Now here it is the restriction site of the EcoR1. Okay, so in the presence of the EcoR1 enzyme, there is a cleavage of this restriction site, and here you can see that, okay, what you can see that when the enzyme is going to act on the restriction site, here G it is base paired with the C, here also the G it is base paired with the C, and now you can see these AA AA and TT, okay, these sequences it don't have any complementary sequence here, okay, and here also this AA and TT it don't have the complementary sequence, that is there is a no hydrogen bonds they are present. So such a sequence, okay, which is going to be generated, that sequence it is going to be called as an the overhang, or it is going to be called as an sticky ends, or it is going to be called as the cohesive ends. Okay, so in this way the enzyme, the EcoR1 enzyme, it is going to generate the 5' overhang, because this overhang or this sticky end or this cohesive end it is present over where, it is present over this 5' end. That's why it is going to be called as an 5' overhang. If such a type of an overhang it is present over, okay, such type of an overhang it is present over the 3' end, then it is going to be called as a 3' overhang or the 3' sticky ends or the 3' cohesive end. Okay, now going towards the next one, nomenclature, how the enzymes they are named. Okay, so take the example EcoR1. Okay, from this EcoR1, E stands for the Escherichia, which is a genera. CO stands for the coli, which is a species, and R it is a strand, and 1 it is a first enzyme isolated from the E. coli. So Eco R1 it is what? It is the first enzyme isolated from the Escherichia coli from the R strain. In the same way, the BAM H1 it stands for the first enzyme isolated from the Bacillus aeruginosa from the H strain. Okay, so the B stands for the bacillus, A stands for the amyloliquefacients, S stands for the S strand, and the 1 stands for the first enzyme isolated from the bacillus amyloliquefacients. Now here it is a chart which is going to show the number of enzyme and its restriction sites, and what type of an restriction site it is going to cleave. So here the enzyme, it is a BAMH1 isolated from the Bacillus amyloliquefaciens, and its restriction site, it is made up of the 6 nucleotide. That's why it is going to be called as the hexacutter. Now you can see GGATCC. How many nucleotides? It is a 6 nucleotide. That's why it is going to be called as an hexacutter. And after cleavage of this restriction site, it is going to produce the 5 prime overhang, or the 5 prime cohesive end, or the 5 prime sticky end. Next one, it is a EcoR1. Okay, it is a Escherichia coli, and its restriction site or the recognition site, it is a GAATTC. And after cleavage, it is going to produce the 5 prime overhang, and as the recognition site, it is consisting of the 6 nucleotides. It is going to be called as an hexacutter. Okay. The next enzyme, it is a HIND3 isolated from the Haemophilus influenzae. It is also a hexacutter, as it is consisting of the 6 nucleotides AAGT, AAGCTT, and it is producing the 5 prime overhang. Next enzyme, it is a PST1. Okay, PST1, it is also a hexacutter, as it is going to have the 6 nucleotides in its recognition sequence in the restriction site, and it is producing here the 3 prime overhang. Okay, it is going to produce the 3 prime overhang. Next one, it is a ALU1. Okay, and it is a He3, and here it is a SMA1. Now ALU1, He3, and SMA1, okay, all these three enzyme, it is going to produce the blunt ends. That is, there is a no overhang, no sticky ends they are present. Now here when you look at this ALU1, okay, its recognition site, it is a AGCT. Okay, and it is going to cleave in between the G and C. So here when there is a cleavage, okay, it is going to separate like how AG and CT. So they, both of them, AG and CT, they are the best paired, and that's why the ends, they will be called as an blunt ends. In the same way, He3, its recognition site, it is a GGCC, and there is a cleavage in between the G and C. Okay, so the ends they are generated, it is a blunt ends. Now when you look at the recognition site or the restriction site, it is made up of how many nucleotides? It is made up of the 4 nucleotides, and as it is made up of the 4 nucleotides, it is going to be called as an tetracutter. Tetra means 4. Okay, so it is going to be called as an tetracutter, and the ends generated by the enzyme, it is the blunt end, or the blunt end, it is also going to be called as an flush ends. Now the SMA1, it is a hexacutter, and it is also going to produce the blunt ends. The next one, it is a 8 base cutters, and it is a not one, and it is a SBF1. It is these two are what? These two, they are the 8 base cutters, and it is going to produce the not one, it is going to produce the 5 prime overhang, and SBF1, it is going to produce the 3 prime overhang. Okay, it is a 8 base cutter means what? It is going to consisting of the 8 nucleotides into its recognition sequence. So here you can see from this chart that there are the enzymes which are going to recognize the different types of the sequences. That sequences, it may be, okay, that sequences, it may consisting of the 4 nucleotide, it may consist of the 6 nucleotide, or it may consisting of the 8 nucleotide. Okay, now when you look at the composition of these recognition sites, okay, when you look at the composition of the recognition sites, the recognition site is rich into the GC sequences. Okay, now here you can see it is a GGCC, here it is a triple G, triple C. Okay, this sequence, the not one sequence, it is a GC, GG, CC, GC. Okay, then you are then your BAMH1 restriction site, it is a GGATCC. Then your EcoR1 GAATTC. Okay, so when you look at overall, okay, overall when you look at these recognition sites, they are rich into the GC sequences. Okay, and accordingly, the how many nucleotides they are consisting of, they are going to be called as an hexacutter, tetracutter, or the 8 base cutter. Okay, I think you have cleared this chart. Now going to the next one, it is a isocysomer. Isosisomers. The isosisomers, they are the enzymes which is having the same sequence specificity and the cutting site. Okay. Now here it is an example of the HPA2. Okay, it is having the sequence CCGG and it is going to cut in between the C and the G. Second one example, it is a MSP1. Its recognition site and the cleavage site, it is the same like the HPA1, HPA2. So these HPA2 and MSP1, these will be called as an isosisomers because they are going to recognize the same sequence and it is going to cleave at the same site. Second one, it is a neosisomers. Neosisomers, they are going to recognize the same sequence, but it is going to cleave at the different sites, okay, or the different point. Now here it is an example of the SMA1 and the XMA1. Now the recognition sequence, it is the same. It is a CCCGGG, and the SMA1, it is going to cut in between the C and this G, but your SMA1, or that is a XMA1, it is going to cleave in between the CC. So this, it is going to be called as the neosisomers. Okay. Next one, it is the star activity. Now in the star activity, what is going to happen that a sequence for the cleavage, it is going to change. Now, when you are doing the restriction digestion, okay, that is you are going to cleave the DNA with the help of the restriction enzyme. At that time, you are using the buffers. Okay, so the buffer, it will have the particular pH and it will have this particular strength. So this pH and the strength of the buffer, it is going to, okay, it is going to affect the activity of the enzyme. When the pH, it is elevated, or when you are using the low ionic strength buffers, at that time, okay, at that time, what is going to be happen? There is alteration of the cleavage site. Second, here when you go for the isolation of the DNA, at that time you are using the organic solvents. Okay, if there are the contaminants of that organic solvent, at that time also there is alteration of the recognition sequence, and that it is going to be called as the star activity. For example, it is a eco R1 asterisk. Okay, it is going to cleave the, okay, eco R1 star activity. It is going to cleave the sequence. It is a NAATTN. Now the N stands for what? Any base. Okay, so here there is one alteration of the recognition sequence. Eco R1, normally it is going to cut the GAATTC sequence, but when there is a elevated pH, that is there is a high pH, or there is a low ionic strength, or when there is a contaminant of the organic solvent, at that time, instead of the GAATTC, it is going to cleave the NAATTN sequence. Okay, so in this way, it is a star activity. I think you may have understood the restriction endonucleases too. If you have cleared if you have liked my video, please subscribe my channel and also share my video with your friends so the knowledge it is going to spread. Thank you.